I wanted to speak first about a few examples. So the scope of the lecture is a little bit narrower than what the title might indicate. So in fact, I'm not going to talk about number theory in general, but mostly about Diophantine equations. These are equations of this form, where you are seeking rational solutions or integral solutions. These are classical Diophantine equations. So the terminology is a little bit misleading because it's not something special about the equation, it's more the solutions. You're interested in integral or rational solutions. So you probably know some solutions to this equation. So I guess I should ask the students. Are you a student? 학생이시죠? Can you give me some solutions? For that first equation, it's easy, right? No? It's too nervous, I think. Some solutions? It's very easy, right? 우리말로 물어보면 좀 나을까요? 너무 긴장한 것 같으니까 그럼 이쪽 학생.
솔루션이 뭐냐고요?
솔루션 좀 줘보라고요, 예를. 1,0 쉽잖아요. 그렇죠. 1,0 좋죠. 또 0,1도 있고 뭐 마이너스 1,0도 있고 뭐 다 많잖아요. 근데 그거는 다 비슷하고 좀 다른 거. 진짜 다른 거. 첫 번째 이퀘이션. 네, 첫 번째 이퀘이션. 아시죠? 그러면 다시 만회할 기회를 드릴 테니까.
아니요.
많잖아요, 저.
연립인 줄 알고.
네. 아, 연립이요? 연립으로 보면 너무 어렵죠. 당연히. 그래서 고민하고 계셨구나. 혹시. 미안해요, 과소평가해서. 하여튼. 첫 번째 이퀘이션, 그러니까 플러스 마이너스 1, 0, 플러스 마이너스 1, 그거 말고도 해부를 알 것 같은데. 모르세요? 5분의 3, 5분의 4 그런 거 있죠? 그렇죠? 또 그거하고도 상당히 다른 것도 있을 또 알 것 같은데 몇 개는 아세요 혹시? 13분의 12, 13분의 5 그런 것들도 있고 그렇죠? 되죠? 생각해 보면은. Okay, so there are solutions like that to the first equation. Like, I guess I wrote equation 0, zeroth equation. So we're mathematicians, so we start counting as 0. How about the equation number 1? What are some solutions for equation number 1? 또, 학생. 0,0. Yeah, very good. 0,0. Very good. That's a good solution. What else? 또, 그 뒤에 학생. There's a few other pretty easy solutions, I think. 6,0, right? 6,0 works. Yeah. Okay, so there are solutions like this. I guess minus 6,0 should also work, right? So those are all fairly easy. And then there are these famous equations, number 2, right? And you may know that in some cases, for example, if A, B, C is 1, there are very few solutions, right? Okay? Okay, so this is the nature of Diophantine equations, and you know a few solutions, you know how to solve some of them. Now, it's quite difficult, of course, for many of such equations to find solutions if you're not given any prior data somehow, right? And sometimes there are many unexpected solutions, so let's look. So here's a solution to the first equation. You may not have known this one, right? And for the second equation, so here's the solution. So these kind of solutions are quite non-trivial to guess, right? It's not like the small ones that we discussed earlier. And there's a method for guessing them. So these methods are geometric in nature. So for the first one, it's very classical. People call it a method of sweeping lines. And the second one, the method is called the chord tangent method. Unfortunately, I'm still very bad at drawing pictures on PDF in LaTeX, so I'll draw the picture on the board. So for that first equation, you just draw this circle. Actually, can you see this? Or maybe it's too dark. Can one? Maybe. Oh, sorry. No, that's not it. 칠판이에요. Okay, good. Right. So this is x squared plus y squared equals 1, right? And we're looking for rational coordinates points, right? On this circle. So we found these 4, and then there were some other suggestions, like there was something like 5분의 3, 5분의 4, and so on, right? Okay, so there were things like this. Now, but there's a way for finding all of them for that first equation. You'll find this in very elementary books on number theory. And this is the method. You consider all of these lines that go through, for example, this point. Consider all the lines. And so here's the point. So when the line has rational slope, something special happens. If you take any line with rational slope, where the slope is rational, then this point that it meets, so let me put it this way. Let's say the slope is t, and you can call this point xt, yt, right? So it will be determined by t. For each slope, you'll get a point, right? And what happens is that whenever the slope is rational, this will be rational. So this is the theorem in this case. You can guess why, right? Because everybody has done this in high school, right? You substitute the equation of the line into the equation of the circle and you find the points, right? And then what happens is that you'll get a quadratic equation, but with rational coefficients. Now normally a quadratic equation with rational coefficients might only have irrational solutions. You're used to this square root popping up everywhere, right? But what happens is that for the equation that you get if you plug in the equation of this line, there's already one solution, x equals minus 1. So the other solution also has to be rational. And then similarly, once x is rational, of course, since the slope is rational, y will also be rational. So that's the idea. It's not so easy to get them both to be rational, but this is a systematic method for doing it. So that's how I found that solution. I think I took t equals about 101 or something like this. I forgot which number it was. Yeah? So you can produce many this way. In particular, you see that for equation 0, there are infinitely many solutions, right? Okay. Now equation 1, it's roughly similar. It's not the same, but it's roughly similar. It's like this. So the picture this time will look something like this. So you'll have this point, this will be minus 6. Yeah? And then if you draw the curve, you get something like this. Now, the way for getting that solution was like this. I think I forgot which solution I used. And somebody should correct me. I think 1236, there's a solution something like this. I may be wrong about this, and I can't do the calculation in my head right now. But so, if this is wrong, correct me later. But anyways, there's one other solution that you can more or less guess by staring at the equation carefully. Yeah? And then you do something very similar to what we did there. Except there's just one difference. This is again fairly elementary number theory. If you sweep through with all lines that go through this point, right? And try to find the points of intersection again. Now there will be 2 points of intersection, right? Because there's a cubic equation. So the fact that this point has rational coordinates doesn't force the other ones to be rational anymore, right? Because these two will still be determined by a quadratic equation. The whole equation will be cubic. It will have one rational solution, x equals 12, and the other ones still may both be irrational, right, in this case. So what does one do? Some of you probably have seen this. The idea is you can't use all lines. You have to use a special line. For example, you draw the tangent line through this point. If you draw the tangent line, then the cubic equation will have a double root at this rational point, right? And then the third one will also be rational in that case. So that's one way of doing it. And then you can draw the tangent line again and keep going. And then once you have two rational points, you can draw secant lines through those 2 points, and then the third point will again be rational by the same logic, right? Yeah. So this is how I found that solution. This you can do by hand up to about that depth, but then when it gets bigger than that, you should use a computer, of course. Right. So this is the method for finding solutions to equations of this sort. Yeah? And you might think, oh, this is very nice. We can find solutions to many, many equations like this in a similar way, and it doesn't work. So for example, if this kind of methodology worked in great generalities, then this other equation, people may have been able to say something about this much more generally, much more easily, but you can't. It doesn't work. Actually, this equation for n equals 4 can be analyzed in a way similar to what we just did for a kind of curious reason. But once n is bigger than 4, somehow this method doesn't work. And you can, again, easily guess why not, right? If you are trying to produce rational solutions by drawing lines, the equation you get when you're trying to find intersections will become of higher and higher degree, right? So it's hard to produce rational solutions starting from 1 or 2 or any fixed number. You see? So that's the situation. The one aspect of why these equations are more difficult than the ones up there. Yeah. So one can say a lot about this, but we'll just focus on 1 or 2 ideas surrounding it. Now, so let me say it in a slightly different way, make the point that I just made in a slightly different way. What we did for the equations 0 and 1 was to draw these pictures of real algebraic curves, you know, the real solutions, and try to use the geometry of those curves. Yeah? And somehow, say, what happens, and so we found those non-trivial solutions this way, but what happens is that for the third equation number 2, I should have labeled it 1, 2, 3 because I keep making mistakes. Anyways, for the ax to the n plus by to the n equals c, the real picture actually turns out not to be very useful. People try to work with the real algebraic curve for a long time, and you can do some things, you know, with the real algebraic curve, but it is something of a fact not easy to come to terms with, that the real picture isn't very useful once you get to equation of higher degree. So, in some sense, we're still stuck on what to do with such equations of high degree. That is to say, if you look at fxy equals 0, say, where the degree of f is bigger than or equal to 4, so far, there seems to be no systematic method for analyzing rational solutions to these equations. So it's a very frustrating situation in number theory and maybe even embarrassing, right? There seems to be a very simple range of problems, but a systematic approach to just solving equations in 2 variables of mildly high degree is non-existent. We don't have a way to do it. So if the students here would like a good problem to think about starting now, you can say, you know, the problem is so easy, you can start thinking about it right now, right? It can eventually lead to important advances in number theory. It doesn't have to be that Fermat equation or something like this. Anything you want, you can start thinking about these kind of equations. We're using elementary techniques and see if it leads to something. Now, the fact is that part of the difficulty is related, well, not to this necessarily to this real algebraic curve picture, but actually to the topology of the complex solution set. Okay, so now we were interested in rational solutions, right? And I pointed out that in some cases you analyze rational solutions using real picture, right? But in fact, to get a full idea of the complexity of the situation, even the real picture isn't enough. Actually, you do have to look at the complex solution set for a moment as well. So take an equation like this, take the complex solution set. And that somehow, the shape of that complex solution set is a measure of the complexity of the arithmetic problem as well. 그게 상당히 이상한 현상인데요. 그러니까 it's a strange phenomenon. that the number theoretical solutions are strongly influenced by the complex solution set, which is a space of some topological space of some sort. In fact, as you know, if we look at this equation inside, what do I mean by the complex solution set? I'm saying let's look at this equation inside C2 now rather than R2, right? Okay. Then an equation like this is the same as two real equations, right? One complex equation is the same as two real equations. And then the real dimension of this space is 4. So when you put two real equations, you'll get the space having dimension 2. So in other words, it's a surface. It's a topological surface. That's what you get. And somehow it's the topology of that surface that influences the nature of the solution set. And the equation 2, or high degree equations, one of the reasons that they're very difficult to analyze is because this topology is complicated. So I'm just summarizing here what I said before. We're interested in integral solutions or rational solutions, but in fact, this topology of the complex solutions becomes very important. So in fact, okay, so you can ignore all of this, but the point is that if you remove a few singular points, possibly, what you get is a complex Riemann surface. So I'll draw a picture again. Except for a few points you might have to remove, what you get when you look at the complex solution set is this kind of thing. Possibly more handles, okay, with some points removed. This is what it typically will look like. So it takes a little bit of work to prove this, that you get this kind of picture. Well, not so difficult. It's about at the level of beginning Riemann surface theory. But anyways, this is the picture you get. And the number of handles you have here, number of handles, is called the genus of the equation. It's called the genus. You look at the complex solution set and look at the topological type of the solution, and depending on how many handles you get the genus of the equation. So for example, the equation 0 had genus 0. That's why I call the equation 0. Equation 1 actually had genus 1. Precisely, equation 0, if you look at it, it becomes a sphere minus 2 points. And equation 1, it became a donut like this minus 1 point. But equation 2, oh sorry, I should have said this is for this genus 2, this is for n equals 4. Equation 2 for n equals 4 becomes a picture like this with, I think, 4 points removed, something like this. So if you look at this picture, of course, this is a more complicated spaces than this too, right? And the lesson, which took about 100 years for number theorists to realize, is that in fact it's that complexity of that space that influences the nature of the solutions. That's what this is a restatement of what I said before. Right. Now here's a big theorem, by the way, which is still the best general theorem we have on this topic. Yeah? That is to say, so let me put the equation back on the board. Maybe I'll put it over here. We're still looking at the solutions to an equation like this, right? Okay. And then notation x sub f, q, this was my notation for the rational solutions. Okay? So that's the rational solutions to this equation. And the big theorem is, theorem of Faltings, is that when you have a picture like this, yeah, for the complex solutions, if the complex solutions gives you a picture like this with at least genus 2, then necessarily there are only finitely many rational solutions. So that's the big theorem. So things are in some sense in a very satisfactory state of affairs because we know this is a finite set, but the difficulty is we have no method for finding that finite set. There's no method for finding it. When I say method, of course, what I mean is a systematic method, yeah, or an algorithm of some sort. Yeah? Because, of course, for a specific equation, you know that it's empty, say, for example, right? So if I told you x to the fourth plus y to the fourth equals minus 1, then you know that there are no solutions, right? So there are situations like that. But it's not a method. It's just that special equation about which we can make that statement. What we would really like is to be have some methodology that whereby we can be handed an f and then come up with a full list of rational solutions. And this we don't have. In fact, a more precise statement is that the example I gave you just now, there are situations, that is, where we can say that the solution set is empty for trivial reasons. And if that's not the case, we don't have any way of approaching these kinds of problems. For example, if there's at least one rational solution, in these cases, if you have any equation having at least one rational solution, it's very difficult to list the full solution set. There are very few results of this sort, even for specific equations. If you have one rational solution, can you tell whether or not that's all of them, for example? It's very hard, it turns out. So that's the current situation. So our state of knowledge about these things is very primitive. So, I mean, nevertheless, it's a very nice theorem because, for example, for these equations, even without Fermat's last theorem or things like that, we knew before that all of these equations have only finitely many solutions because of Faltings theorem. This was known since 1983, say. But it was only in, say, for ABC equals 1, it was only later in 1995 that we knew that there are only these trivial solutions, right? So you see the difference between knowing these finiteness and knowing the big full solution set is very big sometimes. In this case, 12 years, and in some sense, several hundred years, depending on your point of view. You know that it's finite, but finding it can be much harder work, starting from the knowledge of finiteness. Right. So this is the problem. And this is sometimes called the effective model problem. The reason is that this theorem of Faltings that I referred to earlier, this was called the model conjecture before. It was conjectured by Model sometime in the early 20th century. And then Faltings proved it in 1983. So the finiteness itself was a conjecture that was proved by Faltings. So it's a theorem. But the effective version of this problem is still an open problem. What I said just now, earlier. Find a method for computing this as a function of the equation somehow. If you're handed f, find a method that will yield the full solution set. And this is still an open problem, and I think many would agree it's still one of the most important problems in number theory, being able to get at this. Now, so what I was saying, is that many years of experience now indicates that looking at this real algebraic curve seems not to be very useful for this problem. Although some people still believe that this is the right way to go, but that somehow you have to use. So one method for refining the real picture is to consider metric geometry of the real algebraic curves. Consider it as a Riemannian manifold with a lot of other structure, rather than just looking at it as an algebraic curve. That's one method. But as I said, it's not so easy to get results using that idea either. Now, I've already referred to the topology of the complex solution sets as influencing this problem. But as the title of my lecture indicates, one of the key aspects of this story, of the complexity that I want to focus on, is this fact. What complexity am I speaking about? I'm referring to the fact that when the genus is at least 2, the fundamental group of the space is non-abelian. That's one of the different measures of complexity of the equation. You remember what the fundamental group is? When you're given a space, you consider homotopy classes of loops based at some point. So you're given a space like this. And then you consider a group generated by loops of this sort, right? Okay? So That's what the fundamental group is. So for that space over there, okay, I should ask you again. So what's the fundamental group of that space? Free group on 4 generators, right? Free group on 4 generators, very good. And except it's not quite right? Yeah. That's right, quotient by one relation, right? There's a quotient by one relation. There's a free group on 4 generators, except there's one relation, yeah? Anyways, but you probably know that if you take this guy here, yeah, what's the fundamental group in this case? Now it's free group on 2 generators, right? Again with one relation. But that one relation in this case makes the fundamental group what? Abelian, right? In this case it becomes abelian. Here it's still non-abelian. That's the difference. Yeah. By the way, for the sphere, what's the fundamental group? You know, right? What's the fundamental group for the sphere? That's trivial, right? Okay. So you see that these two, the fundamental group is somehow simple, but starting here it starts to get complicated. By the way, the free groups, you may or you may not know, that the free non-abelian groups, not the free abelian group is fairly simple, but the free non-abelian group is a very, very complicated object, although its definition somehow make it look very elementary. But anyways, when we go to free group of, say, 4 generators modular relation or 6 generators modular relation, it's a very complicated group. And that's one of the measures of the complexity of the equation as well. That's what I'm trying to say. Mm-hmm. Oh, sorry, that's the notation I skipped quickly as we were going along. So I meant you take the closure inside projective 2 space. Yeah. But since some people might not like projective space, take that as a notation. Yeah, you have to do a bunch of things. I will skip all of that. That's right. So assume that you're in the simplest case. You don't have to worry about that. Yeah. So anyways, so this is a key fact. So the fact that this is a relevant issue in studying the number theory of the equation, this is a fairly recent development, that is. The fact that the topology is somehow relevant is an old story. But the fact that one should focus on the non-abelian fundamental group as being of particular relevance, this was more or less what was outlined in a letter from Grothendieck to Faltings in 1985, short while after the proof of the model conjecture, short while after the proof of that theorem of Faltings I cited earlier. Grothendieck wrote a letter to Faltings suggesting that this is the thing that you should actually be looking at. This isn't what Faltings looked at. It actually, in some sense, it had nothing to do. Faltings' proof had nothing to do with non-abelian fundamental groups. But then, short while after that, Grothendieck said, well, actually, you're giving the wrong kind of proof. This is like more or less what Grothendieck actually says. You should actually be looking at this kind of thing. And he somewhat explains why, without being very clear. And for me, so for myself personally, that letter is more or less what I've been thinking about all of my mathematical life. It's a complicated story somehow. But anyways, I'll try to give you some indication of what this issue is and how it relates to the model problem. Yeah? How does it relate to the finiteness of points, for one thing, and how does it possibly even relate to the effective model problem. So I'll try to give you some indication of this. Now, first of all, so this is actually the actual topic of my talk. I don't know how well I'll be able to convey this, but maybe I will give you some kind of an interlude. Oh, sorry, there was one more sentence. I forgot about that. Yeah, sorry. So this fundamental group, by the way, here, I should have explained this first. It's the non-abelian fundamental group is related to the fact that one shouldn't be looking at the real numbers. So to solve equations of high degree, of high genus. It's actually the P-adic numbers that are much more useful. Now, some of you may know about the P-adic numbers and some may not. You don't need to know much about it at this level of the lecture. But very roughly, you probably know that there are these rational numbers here that are embedded inside the real numbers, and this is a kind of completion of the rational numbers, right? That's one of the ways of constructing it. So nobody thinks about the real numbers in that way, but you construct it as a completion, right? Normally you think about it as a line, or any ordinary person thinks of it as a line, right? Geometrically. But the completion is the mathematical construction, right? As a set of sequences, say, for example, right? But once you construct it that way in a mathematically rigorous foundation, you find that there are many other ways of completing the rational number. So there's something called the 2-adic numbers, for example. There's something called the 3-adic numbers. There's something called the 5-adic numbers. And you go on, there's something called the 521-adic numbers. There's something called the 691-adic numbers, and so on. So that is to say, there's a P-adic number for each prime P. These are all primes, by the way. You should know a few big primes anyway. Most of us know no prime bigger than 37, I think. But it's good. If you're a mathematician, it's good to be able to name a few larger primes. But anyways, so this is the fact that once you take the rigorous construction of the reals, you find out, that people found out soon afterwards, there are other numbers that are analogous to the reals, but which preserve different kind of information about the rationals. This preserves the usual sense of distance of the rational, but these have different notions of distance on the rationals, having to do with divisibility by the prime number. And so you have this whole range of different completions of the rational. And the point is that similar to the real picture, if we embed Q into any one of these other fields, we get a different geometry that gives us different insight about, say, solutions, rational solutions to Diophantine equations. And that's the idea. And people have used this idea for a long time as well. But the precise form whereby different P-adic embeddings is related to the fundamental group is a relatively new development. Now, I wanted to entertain you briefly with an interlude on the supposedly easier case, which is still very hard. So I was wondering whether I should include this interlude or not, because it really can be completely skipped for this lecture. But to skip it would give a misleading impression of where the research is going. So I will include this. You see, so I've mentioned elliptic curves. So what elliptic curves are, again, many of you probably know, that's the case of genus 1. So, for example, the equation number 1 we had on the first slide, y squared equals x cubed minus 36x. This one is an example of these elliptic curves, right? Equations of that sort. And the topology is that these are always just these single tori with a single point removed when you look at the complex solutions. So in some sense, this is the easier case, as I said. But even here, of course, there are many open problems, and the arithmetic of these curves is the subject of the conjecture of Birch and Sunit-Dyer. So the name is that conjecture is a very famous conjecture, and that may indicate that there are still many difficult open problems regarding even these equations. But let me mention briefly one possible kind of result that people prove for these curves. That is to say, we still don't know a lot about these equations even, but here at least there is a very harmonious conjectural picture. Theorems, still there are not that many. But the conjectural picture is quite believable, and there's a lot of evidence for these conjectures. So the theory is fairly satisfactory, even though results are still lacking. So that's the situation for equations with this set. And the conjectural picture, as I said, all surrounds the conjecture of Birch and Sunit-Dyer. So to just give you a flavor of this, so here's an example. Oh, sorry, I forgot. Before I give you the example, let me mention a key aspect of this equation. So this is actually the famous theorem of Wiles and collaborators, which is also includes the proof of Fermat's last theorem. So somehow the fact that this is related to the equation's higher degree is a little bit of an accident, so you should ignore that for right now. Here, I'm just talking about these type of equations, yeah? Not Fermat type equations at all, even though it was eventually used for those other equations. So this is a completely different issue. The main theorem is that for certain equations of this sort, the complex solutions, which looks like this, looks like a torus, actually can be uniformized. There's a complex analytic surjective map from the complex upper half plane for any such thing. So, except there's one other thing. This uniformization from the upper half plane has just a little property. That's what I'm referring to as arithmetic uniformization. So, which says that the fibers of the map, as you go from the upper half plane to the elliptic curve, has to contain the orbits of one of these arithmetic subgroups of SL2Z. So this is the so-called group of fractional linear transformations acting on the upper half plane. Yeah? And the fibers of the previous map should contain these arithmetic subgroups. So this is a funny condition, but this really was a very big theorem. Yeah? The fact that any elliptic curve of this sort, right, the complex points can be uniformized by the upper half plane in this way. And this was a big breakthrough, of course, in 1995, and many results follow from this. But be that as it may, what I wanted to say about this was that you can use this, for example, to define something called the L function of the elliptic curve. Well, this is a funny formula, so you can look at it or not. Okay? But it doesn't make much sense unless you've actually worked with it. Yeah? What you do is you use that uniformization to pull back to the upper half plane an invariant differential form from the elliptic curve and then integrate it along a path like that. This is the L function of the elliptic curve, so-called. Yeah? And so the reason one should look at such a thing is not at all evident if you haven't been working on it for a while. And it's a very mysterious fact. In some sense, even the people who have been working on it don't really understand why you should be looking at something like this. That's actually it's true. There is something of a mystery to everybody. But the fact is that the arithmetic of the curve is strongly influenced by the value of this function at 1. And essentially, this is the content of the conjectural Birchon-Swinton diagram. That when you look at equations of this sort, you should construct this very strange complex analytic function and look at its value at 1. And that should encode information about that, the rational solutions to the original equation. That's what the conjecture is saying. There's a precise statement about this, but in rough outline, it says that this value should encode something about this. So let me give you an example so this isn't completely abstract. So take this kind of curve, for example. So this my example at the beginning was something of that sort. Yeah? So y squared equals x cubed minus d squared x, where d is an even square free integer. Yeah? So equations of that sort. So notice, for any one of those, there are trivial solutions, right? Similar to what we did over here. So 0, 0, 0, plus minus d. There are these three trivial solutions, right? That stare at you. The question is that even for this, but it's not obvious when it has more, right? Even for this, it's very non-trivial to figure out if it has more solutions or not. There's a theorem about this, quite a strange theorem. Again, even for people who are used to this, it's a strange theorem. So if you compute the L function, the value at 1 for this curve, here's what you get. Okay? So this is just a formula. One can figure this out. Now, LE1, when D is congruent, so it's even, so when you look at it, mod 8 is going to be 2 or 6 mod 8. Since it's also square free, it can't be 4 mod 8. Yeah, so it's going to be 2 mod 8 or 6 mod 8. Yeah. Now, if it's 6 mod 8, the value of the L function defined using the strange integral at 1 will always be 0. When D is congruent to 2 mod 8, this is a formula for it. And what are those AKs? Those are some coefficients that you can construct out of the equation. And this is the formula. So you define it recursively. For prime indices, you define AP to be P plus 1 minus, so what is this quantity? you look at the equation over the finite field Fp and look at the number of solutions there. But you see, this is very easy to compute because a finite field is a finite problem. You just have to consider coordinates, two coordinates in Fp, and see which of them satisfy the equation. So this is very elementary to compute. So you can compute these coefficients AP in this way. Then AP to the R is defined using the lower orders using this recursive formula. But this is only when P doesn't divide 2D, and A plus R for P dividing 2D, you just set to be 0. And then, for M and N relatively prime, A sub Mn is defined by this formula. So if you look at this, right, you don't have to understand it too well. By combining these formula, you know you have a formula for each of these AK for any natural number K. Yeah? So this is a well-defined sequence of numbers. And the statement is that that L function that defined using that integral, when you evaluate at 1, it gives you this series. So this is not so hard to compute, even though it looks complicated. It's actually not that hard to compute that it gets to be this. But what happens is that if you do this value, so for D equals 6, the value is always 1. D congruent to 6 mod 8 is always 1. For these values of D, this may be 0 or not. And so this can vary. Yeah? So it depends. Because you see, if you look at AP, this could in principle be negative or positive. Yeah? So one varies. So this is sometimes 0 and sometimes not. And that's somehow a key issue in analyzing this equation. And there's a great theorem of Colton-Wiles, yeah, that looks like this. This was from 1978. Yeah. That if the value of that L function at 1 is not 0, yeah, then the set of rational solutions is finite. So that was a theorem. Long before any of the Fermat theorem work or related thing, there was this very interesting theorem, which was actually the first case of the proof of the conjecture of Birch-Swinton diode. This was the first, it's a partial, very small part of the conjecture of Birch-Swinton diode, but this was proved. This was the first case that was proved. So, as I said, in fact, what happens is that for these curves, if this value is non-zero, then these trivial solutions are everything. There's no more. Now, it's still a conjecture. The part that's still unknown, even for these curves, is this. If L value at 1 is 0, then the rational solution should be infinite. So that's a conjecture that's still open, even for these curves. So another problem for you to work on. So you might try to think about it just in elementary terms. Maybe there's something you can do, but that's still open. It would already be a big advance. Actually, a tremendously big advance. Nobody knows how to do things like that. So to prove that if the value is 0, then the solution set is infinite. So this case, it turns out, of course, this is the case where D is congruent to 6, yeah, mod 8. So L1 is 0. So that's why we had this other solution. Yeah? This was allowable, yeah, because of the vanishing of the L value. So this is a general philosophy regarding curves of genus 1, that somehow the arithmetic is controlled by the value of strange, actually very mysterious complex analytic functions like this. To be honest and express my opinion, it's a slightly prejudiced opinion, but I don't mind saying it because it makes it more fun if I express a prejudiced opinion, is that I don't like this formulation of the conjecture at all. It's a very strange way of approaching the arithmetic of curves, to define a complex analytic function and try to encode the information. There must be a different way of doing it. That there sounds to be, my feeling has always been that this way of associating an analytic function that's supposed to encode the arithmetic of varieties maybe was a misstep in the 19th century by Dirichlet and related people. Somehow it's the point of view that gained a tremendous amount of influence, and there are great theorems associated to this point of view. But there's some way in which these kind of theorems just don't quite feel right. Yeah? So, okay, I don't entirely believe this statement either, but it's interesting to say it in that way, so that's why I'm saying it. So there's something strange about this formulation. That's another thing to think about. Is there a better way to approach these L function philosophy than the one that's current? But anyways, so in fact, even though I don't like this philosophy too much, I've been essentially, that's all of this is nonsense, but you see, I've been essentially working on trying to generalize this idea to curves of higher genus, even though I don't like it too much. So the point is that the theorem of Coates and Miles itself relies on studying the homology of the elliptic curve. That's the basic idea. So this is now, the notation gets more technical, but what you have to do is you have to look at the elliptic curve, homology of the elliptic curve with P-adic coefficient. And then, that homology group, once you take P-adic coefficients, what happens is that the Galois group, the automorphism group of the algebraic numbers, Q bar, acts on that homology group. And this is a Galois homology group of some sort. And the conjecture of Wettstein-Smith and Dyer, the most important part of it is that when you take the set of rational points of the elliptic curve, one already knows that that forms a group. So you make a QP vector space out of it in this way. So this is a P-adic picture of some sort, not a real picture. Then it becomes isomorphic to this Galois homology group. And what they actually prove, say Coates and Miles actually prove, is that this L value controls the size of this Galois homology group. And this is always the approach to whatever you can prove about the arithmetic of elliptic curves. And somehow, well, we've been trying to generalize these ideas to other varieties, especially curves of higher genus. And what you need to do is you have to substitute the homology group here. You have to replace it by the fundamental group. That's the idea, in order to study curves of higher genus. And this is more or less what's suggested by Grothendieck in the letter to Faltings, although it doesn't appear that way. So for me, it took me many years to figure out that that's what Grothendieck was trying to say, but that does seem to be the case. So I don't know how much of a feeling I can give for this, but maybe because there's not too much time, so unfortunately I prepared about 80 pages of slides, I think. But so we'll just, but I will give you a little feeling for how these can be, what's actually used regarding the fundamental group. So you have to do a little bit more than the fundamental group. So I'm not going to explain almost anything, but as I said, I'll explain to you the idea that goes into using these homotopy groups for studying points. And here you actually have to look at something called the fundamental groupoid. This is where we take two base points instead of one. So this is sometimes called, so when you take this with for all A and B, you sometimes call it the fundamental groupoid. That is to say, instead of looking at loops based at one point, you take 2 points, A and B, and you look at paths from A to B and homotopy classes of such things inside the space. So that's pi 1 of A, B, A comma B. And the thing is, if you have the homotopy classes of paths from A to B and then those from B to C, you can compose them to get homotopy classes of paths from A to C. This is the structure you get when you consider all the pairs of base points at once. So there's somehow a coherent way in which these things can be thought of together as you vary the 2 points, A and B. Well, what's especially important for us is that if we fix one base point so that you get actual, so the thing is, this guy is not a group, right? There's no way to compose 2 of them in the same place. But if you consider the loops at A, you can compose any one of those with a path and get another path, right? So in other words, there's an action of this group based at B on the space of paths for any other point, X. There's an action. So in fact, there's a simply transitive action. So it's essentially the same, except this one doesn't have an origin. It's not a group of any canonical sort. And the idea is, for studying, using homotopy groups to study points, is that we can use these spaces with action of the fundamental group. You can view these as varying with the point X. And somehow, when X is a rational point, these sets have special properties. And by studying the special properties of the sets that you get when X is a rational point, you seem to get insight on the Diophantine problems of the equation you started out with. That's the idea. And here, somehow the non-abelian nature plays a very constructive role. Yeah? So in geometric language, what each of these sets is, it's what a differential geometer would call a principal bundle for this group. It's a set with a transitive action of this group. So that's called the principal bundle. Usually it's over a non-trivial space. But even though this is, in some sense, we're starting out in a very trivial setting, it's something that a geometer would call a principal bundle for the group. And we study these principal bundles and view them as encoding the data of the point. Yeah? So this is all I said. I've said all of this already. Now, of course, we have to distinguish the rational points somehow, right, from arbitrary complex points. And here, the P-adic numbers start to play a very important role again. So I'm not going to go into this very much for lack of time, but what you have to do is you have to take the group and linearize it in the P-adic in various ways. One thing is to take this group algebra, for example, that you can do with any discrete group, and you get a QP algebra instead of the group that you started out with. Yeah? Now, then you have to do a bunch of other operations that I won't describe very much. So this is all the roughly technical details. But I will mention what the result is at the end. What you get is, you can start, this you can do with any discrete group. Okay, so this is the relevant slide. So you can start with the fundamental group, and there's a way to put it inside a large, becomes a large algebraic group defined over the P-adic numbers. This is called a P-adic completion. This is one of the many different notions of P-adic completions of an arbitrary group. So you start out with the fundamental group of a space, and there's a way to canonically send it into a P-adic algebraic group. And this kind of thing was studied already by topologists substantially. There's a way to turn the fundamental group into an algebraic group, and that gives it a more geometric structure. It's somehow a weaker invariant than the fundamental group itself, but for the purposes of arithmetic geometry, it turns out to be very convenient. So you see, so the group can be completed, but also these principal bundles of paths can also be completed to turn into principal, but be turned into principal bundle for this algebraic group. And the point is that when you do this through some mysterious process again, but this isn't very mysterious, it's just for the language, is that when you've done all this, now you can start distinguishing the rational points. That is to say, when the base point and the point x are both rational, when you've done this completion business, then this guy, when both of these are rational, they admit an action of the Galois group of Q bar over Q. This follows from the tau topology that some of you came to study a few weeks ago. There's a way to interpret all these constructions within the tau topology in such a way that you see that you figure out how to distinguish rational points among complex points. That somehow, when these are both rational, this carries a natural action of the Galois group of Q bar over Q. So this is a very mysterious fact from the point of view of topology, but from the point of view of the arithmetic topology of it developed by Grothendieck is somehow very natural. So that's what distinguishes the rational points from complex points. The principal bundles that you get from rational points have a Galois action. That's the idea. So, here's an important fact. You can ignore most of this, but basically what I'm trying to say is that what happens is that if you take it together with the Galois action, these principal bundles actually identify the point, essentially. So actually, you may have to take a few primes. You can ignore that fact right now. But essentially, whenever you have two of these principal bundles isomorphic to each other with the Galois action, then the points have to be the same. So you can actually safely encode points using these principal bundles. So that's one fact. But the second more important fact is that these principal bundles can be all put together into one moduli space, one big structure. So there's a moduli space of principal bundles for this pro-algebraic fundamental group. But this is an algebraic variety over QP. And that's the power of this approach. That somehow the points of the curve, which are somewhat of a discrete set, become embedded inside a large algebraic variety. And you can try to use that variety instead now to study the points. And this is a kind of geometry which only comes through when you use the P-adics and this non-abelian fundamental group. So let me say again, you start from a rational point on the curve and you associate to it a principal bundle of path. And it has a Galois, so you can so it defines a point inside this moduli space of principal bundles, which is defined in a strange way using Galois cohomology. But it turns out to be a pro-algebraic variety that admits a map from the rational points of the curve. Now, what you have to do is make these things even more P-adic. So I'm going to skip all of these slides and just show you one thing. What happens at the end of the day is like this. You start with, you're interested in the rational points of the equation, rational points of the curve. Now, as I said, instead of going to the reals, you go to the P-adic picture. So you first look at the P-adic solutions now instead of the real solution. And when you do that, what happens is that it fits harmoniously into a diagram of this sort. This is this moduli space of principal bundles I mentioned earlier. But both of them sit inside an infinite dimensional vector space over the Q P-adics. There's a very large affine space over the P-adics which contain both of this. And what you can prove in great generality, not always yet, but at least in substantial generality to be, not great generality, let me take that back, but substantial generality to be interesting at this point, is that in this picture, where a lot of more structure arises, much more structure arises than in the real picture, namely, you can prove in a lot of cases that these two spaces sitting inside this infinite dimensional P-adic space, the intersection is actually finite. And that's an explanation for the finiteness of the points, is that this variety and the P-adic points of the curve inside a very large P-adic affine space have finite intersection. And that's an approach to proving finiteness. Yeah? So here's what I wrote. I'm rewriting it. The rational points can sit inside the intersection of the P-adic point with an algebraic subvariety of this P-adic space in such a way that the intersection is finite. For example, for these Fermat equations, you can show that that intersection is actually finite and deduce from this the finiteness of point. But actually, the general idea is that, well, so there's one remark. So this I won't be able to explain at all. You prove the finiteness of this space using an L function of some sort, a P-adic L function, not a complex L function. There's a P-adic version of that L function that goes into the finiteness of this set, even for a curve of higher genus. So this is the new phenomenon that extends the Breusch-Swenderson diet philosophy. That somehow finiteness of these kind of varieties parametrizing points should be related to an L function. But what we hope for is even more, that in some sense. Namely, what we would like is to view this intersection as being a computable subset of this P-adic space. And that's the key thing. Because, you see, you can compute, there's a way to use analytic function theory over the P-adic number to compute the image of the P-adic points of the curve. That one can do, except it becomes an analytic subspace, P-adic analytic subspace. This other thing, this parameter space, this moduli space of principal bundle is an algebraic space. So in principle, although I can't make this at all precise at the moment, except for very few examples, in principle, this intersection should be a computable space. And so that's what I would like to do at the moment, or what more or less still thinking about, is I'm trying to view this intersection as being a computable approximation to the actual rational points, constructed using P-adic algebraic geometry. Now, so you see, but if you can do this, in principle, you resolve the effective model problem, because this guy is a subset. So if you've computed this set completely, now you can see which one of them are actually points now just by trying out the possibilities. So in some sense, this is being able to compute this set is already good enough for computing the points. So that's the strategy. Now, so far, all I've managed to do is to prove the finiteness of this intersection in at least a large number of case examples and subcases of the general. But what remains to be done, of course, there's still a lot of, we're very far from a resolution of the effective model problem. That's why I said at the beginning that you should think about it. It's still a wide open problem. But what I wanted to outline today was just one approach, using the P-adic geometry of these moduli spaces. But in fact, it seems to, at the moment, really computing this, well, there's some strategy in place, which I'd be happy to discuss in detail to anyone who's interested, with anyone who's interested. But it seems to require understanding some aspects of Grothendieck's ideas of Non-abelian geometry from the 1980s in great deal more detail. But at the moment,